All right, everyone. Welcome to another episode of the TWiML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Bean Kim, a staff research scientist at Google Brain and an ICLR 2022 invited speaker. Before we get into today's conversation, though, I encourage you to head over to Apple Podcasts or your listening platform of choice and leave us a 5-star rating and review if you enjoy the show. Bean, welcome to the podcast.
Thank you, Sam. Thanks for having me. It's an honor to be here.
I'm really looking forward to our conversation, and I would love to have you start by introducing yourself to our audience, sharing a bit about your background, and letting us know how you came into the field of machine learning.
Yeah, sure. I'm a staff research scientist at Brain. I grew up in South Korea. I majored in mechanical engineering back in the day until I came to MIT for grad school. I made some robots initially. Then until I realized robots are so cool, however, limited by physical, like just the time that you have to spend to make the robot. And I thought, you know what, if I just remove the physical aspect of this research and just go with the brain, I can go faster. I can do many things at the same time. Computers can do things while I'm sleeping. So I switched to machine learning and did a PhD from MIT. Then I went through some other jobs and landed in Brain.
And so tell us a little bit about your current research focus. What are the things that you enjoy thinking about?
Yeah. So for many years, I've been singularly focused on interpretability, which is kind of an umbrella term for things starting from how do you understand the data distribution that you're about to train your model on to building inherently interpretable models. Like you design model from scratch, embed rules or logic to make sure that you can understand when the model is trained, and all the way to post-hoc interpretability methods. Like you have already a model, somebody gave it to you, and you can't really change the model. Then what do? Can we use gradients and other things to extract some explanations? So that's what I've been really corely focused on for like the last 10 plus years. And recently I've made a little bit of transition thinking about, okay, we've come this far developing lots of engineering tools to provide explanations. What are we missing? What do we have to do? What is the gap to fill in order for us to move to the next level? And that's what I talk about in ICLR keynote this year about, well, what we really need to do is to parallelize what we do with engineering effort and science. So engineering effort is making tools, perhaps in absence of principles, you just kind of try things out and see what works out, build a lot of tests around it. Whereas science is approaching this complex mechanism called neural network or machine learning models or AI as an organism that we want to study. So go ahead and probe them, analyze their behaviors to see what comes out. Like pretend that this is something that we build a hypothesis and build tests and data and analysis structure around it in order to gain more understanding about this unknown object. So I talk a lot about that in my keynote.
Your keynote, which is titled Beyond Interpretability, as you're describing, developing a language to shape our relationships with AI. Before we do go beyond interpretability, though, I'm wondering if it makes sense to start by having you characterize where we are as an industry and community with interpretability. What's the best way to characterize the current state of the art or the state of the field?
There's a lot of needs and passion and requirements
We're not
in the
fully there
world.
yet, right?
We're definitely not fully there yet. In fact, we're quite far away from it.
Mm-hmm.
Some of my work, I kind of took this, course, if you call like a journey together with the community. I feel like I exactly
Mm-hmm.
was at the position where this is so exciting. We can do so much things and did a lot of things. And then I
Mm-hmm.
was at one point in 2018 in Europe's paper, we share our a little shocking discovery that showed that a lot of interpretability methods that we've been using and deployed are not actually showing what you think it's showing. So to a TLDR of that paper is that when you show an explanation from a trained model and you randomize that model, so go in there, just mess it up, and so now the model is garbage, and show explanations from that model, You can't tell them apart. As a human, you can't tell them apart. As a computer, oftentimes you also can't tell them apart.
That was a big paper.
Right, and that was, it received both very enthusiastic and people, some people who didn't like what they're reading, right? Because we had this trust and passion around these methods, and including myself, I test the own method that I developed, and to my surprise and disappointment, that the methods that I worked on also don't really pass that sanity check test, what we call. Um, and since then, I think we've been, as a community, many smart people smarter than me, joined to think really carefully about what does it mean to make progress. It's not just about making a reasonable and convincing picture of a bird and show an explanation of why that was a bird. Much more beyond that, we have to rigorously validate what we're seeing. We have to conduct human experiments to make sure that what we hope to happen actually happens with the human. So if, for example, this might be a good segue to also talk about one of my paper, this conference at ICLR, where we argue that if your goal is to detect spurious correlation, then existing methods won't work for you unless you know what that spurious correlations are already. So just the community has been thinking a lot about, that's just an example of many other work that start to think about what is a task that we can use this explanation for, and what are the tasks we simply cannot and should not.
In terms of, do you have a sense for, in practice and in industry practice, kind of what are the techniques that folks are using, um, and kind of the state of the field from that perspective? And I ask that mostly because, some of the first methods that I remember hearing about are like Lime and Shap, and those are still the ones that I hear about. Like, uh, is it that I'm not hearing and there's this rich field of things that folks are doing, or are those still the ones that are most used in practice? Do you have a sense for that?
Yeah, I've seen many methods used across Google and other industry. Just, people pick their favorites, and I should mention that, the conclusion of our study that I just mentioned, 2018 sanity check paper, isn't to conclude, okay, all these methods, don't use it. It's not that. The conclusion is that we don't yet understand what these explanations are showing, what information these explanations have. And so if your goal is to, for example, just look at candidates of features that might have been used in model prediction, then perhaps these methods do work for you. In fact, we have plenty of other papers that showed they present these explanations in front of doctors, like actual doctors, and show that, yes, they do help. So it's not to say, these a family of methods, we should throw them away. It's not. It's just to say we should be very careful. We should build a lot of tests around it to make sure that it fits your bill of what you're trying to do. So to your question, I think there, and exactly to follow to what I just said, it really depends on what you're trying to do. So sometimes Lime and Shab, Lime is a very simple method, elegant, simple, but that simplicity also implies that if your decision boundary is very curvy, for example, very complex, fitting a linear function in any of the local area is not going to be a good approximation of how your model works. So in that cases, it will not be the best friend for you. Other cases, there are computationally really expensive methods, and if your task has to be something that decision has to make very quickly, that's not going to work for you because it's just simply so slow. It doesn't work for what you're trying to do. So I've seen many family of methods like those, GradChem, in fact, SmoothGrad also used in many domains, like TCAV used many. I haven't seen a single method that works for everybody. And I suspect there will never be a single method that's going to work for everybody.
Mm, awesome. Awesome. And so your talk beyond interpretability, you kind of organize that around these core ideas of studying machines in isolation. And you spoke a little bit to that, studying machines in conjunction with humans, and then this kind of broader idea of alignment. Let's maybe go through those. When you talk about studying machines with in isolation, You're talking about applying the scientific method to studying the machine learning methods we're building. Speak more about some of the methods that you've explored and the way you think about that category.
Yeah, this is the category that I'm super excited about because there's so much work we can do in this, and just so little has been explored. And the things that I talk about in this talk, Gestalt, is just one of many, many, many centuries old studies after studies about humans. This is just one tiny bit of it, not even 0.001%. And that should just kind of hopefully give you a scope of what I'm talking about when I say studying machines as a scientific object and leverage studies done on humans. We've done many, many studies on humans. Biases, perceptual biases, cognitive biases, or just capability, what we can see and what we cannot see.
So there's a Gestalt study that was a historical Gestalt study from psychology. Was it psychology? And you applied similar ideas to studying machine
That's
learning
right.
models?
Yeah, that's right. So I can tell you a little more about what I exactly did. So Gestalt
Okay.
phenomenon, for those who are familiar with it, is something that is very strong phenomenon that, for example, I show you this triangle. Actually, just think about Amazon logo, right? The Amazon logo has this arrow hidden inside of it. It's called A to Z and it's point at it. FedEx logo actually has also this arrow embedded inside. And those design decisions are essentially based on a group of strong perceptual phenomena called the Gestalt phenomenon. And designers to this day leverage those very strong phenomenon to make visually appealing things. The one specific rule of Gestalt rule, if you make if Gestalt principles or law that we study is a closure effect, which is if I show you three Pac-Mans that align nicely, human eyes cannot help yourself but seeing a triangle, even though there's no triangle. And we are our core question of that paper was, well, does neural network have the same thing? Because if it does, that says something about how our brain works versus how neural network brain works. And you can imagine that's just the beginning of so many other studies that we've done on humans. If I give you a high number, for example, a really famous example Danny Kahneman spoke, talks about if I give you a high number of any kind, like I just say, how many trees do you think we have in Seattle? And you give them a number. Then I ask you a completely unrelated question. Let's say, how many people crossed borders between United States and Canada or something?
My answer is biased higher.
Exactly. Yeah.
Right.
And it's like such a robust statistical phenomenon that it's like so embedded in us. So then the
Mm-hmm.
question is, what are those embedded inherent biases or phenomenon that neural network has? We
Mm-hmm.
have no idea. We just have no idea. And there's so much studies we can do to just literally leverage what we did in humans and just ask machines, craft a design experiment really well and do that experiment to see what happens in machines.
Now, when you're talking about the Gestalt phenomenon in particular, and this example of the Pac-Man and the triangle, are you trying to conduct like literally that specific experiment, meaning a visual experiment and things like Pac-Man and triangles? Because it raises for me the question, what does it even mean for the machine to be doing what the human is doing?
I thought you were going to ask a slightly different question. Also, the two both are interesting questions. So let me ask you a question first. What does it even mean the machine to be doing what humans are doing?
Yeah, just to elaborate, I'm thinking of as we first started to build deep networks, some of the early studies like Deep Dream and others like looked at the early layers of the network and found, textures here and shapes here. Is it like trying to introspect networks and see if we've got a triangle somewhere or something else?
No, it's a lot more global understanding of the object. So let's say we didn't do this in the paper, but let's say we did the following, and I can tell you what that might imply. So let's say I showed in the paper, yeah, Gestalt, the network has a Gestalt effect, and which means that we don't even have to occlude things in an image in order for it to learn how to fill in the gap. Because you know what? If I put a triangle and put something on top of it, and now network can only see parts of the triangle, we already know that network will fill in that gap. And what that means, that might have an implication for the way that we augment the data. The data augmentation, we intentionally rotate and shift or blow up the image or put occlusion on top of it to make sure that network can be robust to these changes. Perhaps you don't have to do that. If you know enough about what the network is already capable of, maybe that could inform data augmentation. And that's just a small example of many things that will guide our decisions when we develop these neural networks. What are the gaps that we should really teach them to, because they don't have it already inherently, and what are the things we should rather we don't have to worry about because it already has some architecture, something about the way we built it already builds in those capabilities.
And so, what are some examples of experiments that you ran to try to demonstrate this? And
Yeah.
maybe before that, what was the question that you thought I was going to ask?
Yes, so I thought you were gonna ask, in traditional Gestalt phenomenon, the way that they test humans is response time. So they put some distracting objects in the screen, and they put a Gestalt triangle and say, "Where's the Gestalt triangle?" or "Where's this anchor thing that how fast they can find it?" So I thought you're gonna ask, how did you test that in neural network? Because that's, I think, the core challenge of doing what what I am excited about doing to in order to bring test experiments that's done on humans to be done for neural networks. You would have to think very carefully about, okay, we can't really measure response time because there's no such thing in neural network. How would you design an experiment such that you can still measure the effect robustly but convincingly? So things that we did a lot of testing into, okay, the way that we measure is this simple metric of closure measure, what we call closure measure. Now, what could go wrong? Would it go wrong if I have these are some of the details, but there are some confounding factors that we should really rule out and test that metric with those potential confoundings to make sure that we're not fooling ourselves, that this metric actually faithfully measure what we want to measure.
Can you explain the metric before talking through some of the confounding factors?
Yeah, it's actually pretty simple. So metric itself is a cosine similarity between two pairs. So first pair is a Gestalt triangle, which invokes that closure phenomenon, to full triangle. So this measures how similar is it to the neural network's embedding space, how similar. And we subtract that cosine similarity with a what we call disordered triangle. So the same Pac-Man, but Pac-Mans are now slightly rotated so that you no longer see the triangle. And similarly between that disordered triangle to the full triangle. And we just subtract the two. And that's all there is really. And we do this for every layer and every bottleneck layers. Because for the ResNet, if there's speed connection, you make sure that every information is coming to that layer. For the confoundings, now many things can go wrong. So, for example, if I make if I don't control for the location of this triangle, for example, when I compare the Gestalt triangle to full triangle, if their literal pixel overlap is a lot more than this ordered triangle, that's a problem, right? Because it's literally the same. It's just this pure pixel overlap is going to be a confounding factor. So, because in neural network, same thing in the same place is gonna think that these two things are similar, and it's not going to abstract out to read our intention, which is to express, well, here are incomplete triangle versus complete triangles. So what we do is we change the background color, we rotate them around, we in this way, and both in local theta, which we call, we control for all that and measure the average effect.
I'm not sure that we covered this, but the presumption being the result is you identified that this effect is present in neural networks.
That's right, but
how do you characterize it to a certain degree, or what's the interesting, what's the degree, I guess?
Yeah, so the interesting nugget in this is that it only exists when the network is able to generalize. So if, let's say, I have a network that was overfitted to some random labels, which we can totally do. We can achieve up to 90-something% accuracy. If I give you a random label, it's happily overfit. But test time, it doesn't know how to generalize. It never learned what is the meaning of, say, frog or cat. those networks do not show the closure effect. It's only the regularly trained network. We also try to keep the label correct, but instead shuffle the pixels. So that means I am destroying the local features and train the network. Again, it is happy to overfit the data because again, labels are correct, but pixels are shuffled. If there is some statistical patterns across the classes. For example, all the cats, the average value of pixels are 0.5, whereas all the dogs are 0.3. So our question was, would neural network leverage that? Neural network train those destroyed local structure, will it still have closure effect? Because if it does, it's not the spatial meaningfulness that causes closure effect. It's something else. It's something else we don't know, and that's something we must investigate. It turns out that if you destroy the local feature, it does not have closure effect. So you might ask, okay, so what does that mean? What does that mean ultimately? Like, why are we doing this? So
Yeah.
ultimately, my studies like this, I think, will lead to insights such as, for example, does that mean that if we build in more human-like perception in neural network when we design this network, LLMs, vision language model, whatever, maybe that means we will help generalization. Now, there's a huge logical jump that I made there because arrow this way, causal analysis this way doesn't mean the other way. However, a lot of studies that could perhaps show that relationship or absence of that relationship could really guide us designing these models, because at the end of the day, we're the ones making decisions what to make next.
Within this broad category of studying machines and isolation, that's just one of the studies that you've conducted. What are some others?
Yeah, so in another study that I share, it's a preliminary results, but this is in that work we think about explanation, the saliency methods, which is the target of the topic of discussion in the sanity check paper, that where we show that trained network, untrained network, you can tell the difference in this saliency map based family of explanation. So we kind of take a deeper dive into that. So then our question in that paper was, okay, so humans can tell the difference, but maybe the information is there, it's just that we can tell. And perhaps the other way around is true too. What if there's information that human can tell but machines can't? So in that paper we show both of the information. So it turns out that if I train a model with the same data, same architecture, but just different seeds. So now I have two models that roughly achieve the same accuracy, but just literally different seeds and different weights. When I get explanations, humans can't tell the difference. They look the same. Like I looked at many of those, same. But for neural network, it can tell which explanation came from which model close to perfection, close to 99%, 96, more than 96% accuracy. So that's like concrete evidence of some information that humans cannot read off of these explanations, but it's there.
This paper characterizes that effect as a fingerprinting of the model. Does that have implications in kind of adversarial, data leakage and questions like that, or are those tangential to the kinds of things you're thinking about?
I think it has implications to that.
Mm-hmm.
But in this work, we focus on explanations alone. That what sort of fingerprints of the model we show that one can read off of the explanation. So, for example, you can imagine. Actually, now you said it. Now I think actually there's a better more link to that. So, for example, there has been work that shows if you just give me explanations, I can actually completely reconstruct a model. I think this is work from many years ago by Moritz Hart's group in when he was in Berkeley. That and what does that mean? Well, that means that if somebody requires me to provide all the explanations for the input data that customers are using, then that could be used to reverse engineer preparatory information, and intellectual property gets really a big question. And I think that's what you were referring to.
And further, there's other results that suggest that, because if we're talking about large models that can memorize data, there's actually training data that can leak into the model. And if that leaks out through explanations, then you're also exposing the potentially private information.
That's right. And Carolina Uller's work from MIT showed that this also happens in VAE models where you can completely reconstruct every single training data because they're attracting points of the network. You can 100%. And apparently this phenomenon is widely common. Nicholas Papernot's paper, Nicholas Carlini's paper all show that this leakage, not about explanation, but just the leakage of the training data completely is possible. So that all should really hint us that there's just so much we don't know about neural
Yeah.
network. And all these studies are super useful, but somebody should also think about, okay, well, let's just go back to the drawing board, zero, beginning, and consider this as an alien. And let's think about how we can study this alien, because there's just simply so much to study. We need a lot of different approaches to study this important alien.
And so this first category that we've talked about is, hey, we've got the alien in a room and we're just kind of, probing and studying the alien. Is the studying machines with humans, is that more looking at the alien in the context of collaborating or working with humans?
That's right.
To
That's right.
extend the analogy.
Yes, exactly. That's right. And I think we should go one step forward. So a lot of people talk about collaborating with machines and how we can leverage each other's intelligence and augmented intelligence and so on. But in fact, I think what's perhaps more important to recognize is that as we interact with these machines and work with AI and live in this society where every single thing that we do or somehow some AI models are behind them, or most of it anyway, we should know that that is changing our behavior. That's changing us. It's changing the society. Take Twitter, take YouTube, whatever. People spend enormous amount of time on social media. Who decides what you see? Who decides what you see from which you make a decision about your life, about your career, how what you think, how angry you are or how happy you are? That ecosystem between machines and humans, it's not just collaborations and leveraging each other. It's a whole world that we're now living with AI. And the language aspect of my talk, how I uh, think that this language must be developed, that we should put force together to develop this language. And I even think that once we develop this language, this might be something we are taught in school for kids as they learn math in high school and middle school. Maybe this is another language that they will learn in schools, because it's so important, so that we have effective ways to manage and communicate with these machines. So pulling back
Wait, I
again,
was curious,
ecosystem.
why you characterize it as a language, as opposed to a set of principles or foundational understanding about using machines. What makes you think of it as a language or a communication vehicle?
It, representational differences. So
Mm,
if we have same representation as a humans, we can
hmm.
agree on a principle because the underlying vocabularies that exercises those principles, we agree. We know that you and I know we live a life and we live and die. We live under the constraints of gravity. We all know that, right? We have common understanding. With the machines, we don't have that. So that means even if we have a principle defined in our own language, we may not be able to communicate what that really means to machines. We even have a hard time communicating with each other what, for example, fairness and fair justice means. And the challenge is so high, I believe that in order to just really fill that gaps in our representational spaces, it would have to be back and forth. It would have to be a conversation. And to have a conversation, we need rich language that both of us can express what we really mean. And that's why language is important.
Tell us a bit about your research program that explores some of these ideas.
Yeah, so I must say that we're at the beginning of a huge effort that we as a community, I hope that we will push on, and lots of folks already have thought about this. So the to build this language, we have to study aliens as or AI models as an object of scientific study, and in not just that in isolation, but also in this whole ecosystem between machines and humans. We live in an ecosystem, we influence each other, we should study that interaction very carefully. But in addition to that, humans have amazing capacity to learn new things. We should expand what we know. This is a great opportunity to meet a coworker who is sometimes smarter than me, you're thinking about your network, who could really show us how to view a problem that we've been trying to solve from a different angle. And that could really inspire us to see the solution that we didn't perhaps previously saw before. So expanding what we know is another branch of this research program that I am envisioning. And some of those work that I talked about in Keynote is AlphaZero, thinking about AlphaZero, the superhuman network that plays chess better than any other humans. How do we go about, can we do in-depth study in this amazing network to see how do we interpret them? What does it know and what does it not know? How much of our representational space overlap?
Yeah, what's your sense for how far we are there? How far we are with that in the case of AlphaZero?
We're far away. I think the answers to a lot of those questions,
All of
this
the
is why
far
it's
questions were far.
research.
Yeah, yeah.
Yeah, it's why it's research, and it's why I am excited to pursue this direction for, probably first. I hope that before end of my day, I would see some a lot different than where we are now. But we are far away. But the things that we discovered in that work is already really interesting and frankly encouraging. So when we started that project, we have this AlphaZero network. Only thing that we knew about that is that it plays chess really, really well. It can beat the Stockfish engine, which is arguably the best chess engine in the world. And note that the chess engine, uh, human player, it's very hard for any human players to beat the chess engine. So this is arguably a very, very good machine. So when we started the project, we weren't sure what we're going to find. We had ideas that, okay, well, let's first try to detect human chess concepts in this network and see if it's there at all. And we honestly thought, we don't know what will happen. How much, like, will we find 30% of a human concepts, 20%, 80%? And we ended up finding quite identifying these human concepts a lot in AlphaZero, which is encouraging news, because that means that at least some concept that at least correlates with how we understand chess, how we play chess, exists in AlphaZero. That's a great news as a common ground to start to expand what we know. So in the follow-up work that we're going to do this summer and next year, kind of a long-term project, is with this amazing former professional chess player, also PhD student in machine learning. She's going to join. Her name is Lisa Shutt. She's going to join us to work on this problem of, okay, now we have an expert chess player who also knows machine learning. How can we discover new concepts that we didn't know before?
What are some other work that you're seeing that in the machines with humans category? You mentioned that you're early on in that part of the research. Are there other examples of things that you're looking at there?
Yeah, so I would love to talk about art project that we've done in as a part of expanding what we know. This is human and machine collaborating together to inspire each other. Uh, so I have a long passion for art related projects because my aunt is an artist in Paris. My mom is an artist. I was just naturally dragged to something that that are just beautiful to see, beautiful to feel and think about. So this project came out of the art and culture team at Google, and with a Nord project, who are amazing three designers and artists in London. And we had this idea of, okay, what if we use the misalignment between how machines view the world? When I show you this flower, would machine also think it's pretty? Would machine think it's very small? Would machine think it's purple? And is it inspiring? Does it inspire it springtime of the year? Or would it think about something else? And what if communicate something to the machine and say, "Hey, machine, I think this is pretty. I think this is makes me think about babies because it's a small plant. What do you think, machine?" And machine comes back with other images from different pool that say, hey, Bean, I think these are images that inspires me when you talk about that flower. And there's this communication back and forth from which I get inspired by say, oh, interesting. So you were thinking ocean for some reason from this flower. I can kind of say that inspires me. This one time I was in the ocean, blah, blah, blah. So that communication, which we call mood board. Well, it's a standard word, but we call mood board search and concept camera is some tools that we built to enable this communication, which we are all open sourcing in a couple of weeks. And I think directions like that, like Deep Dream, you talked about Deep Dream. There has been art projects around Deep Dream to inspire humans. Directions like that, art project, music. We are hoping to also do some music projects. Are exciting because it's also about not just thinking about task, prediction. It's also about how can we enrich human, us and artists and other people behind a machine learning community to leverage this tool. I think that's extremely exciting.
In the case of that art project, Concept Camera, I'm envisioning you've got some embedding space of images and you've got your little plant. You find where it is in that embedding space or what's closest to it. And then you kind of walk the neighborhood to see what's around it. And that's what the machine is thinking of. Is that along the
It's
lines
very
of the way
similar.
you've, okay.
Yeah, it's very similar. So I can give you an example of what one artist, we hired artists to build artistic concept. It's not just the one
Okay.
flower. And one of the concept that she built was, this was actually one of our engineers. She built a concept of father. It reminded me of all the images she collected reminded her of her father who passed. And it consists of images like ocean, maybe some blurry leaves. It's very diverse set of images. And from that, such an abstract concept, what machines, we take all those abstract concepts and build a concept vector from those images in the embedding space as you described, and then find other images from a different pool, maybe by cropping or blowing up some part of the image or removing some part of the image to identify where does this concept present in other set of images. And that's how we create the conversation.
Talk a little bit about is there an interactive element of the conversation? Is that just sequentially kind of choosing another image or is there another framing for that?
Yeah. So we do, there's a lot of interaction. So after machines came back in with a set of images, you can upvote or downvote to indicate, no, that's not what I meant. Yes, more of these. You can crop and scale the images to showcase, this is really what I meant. And you can go back and forth infinitely. Images are such a powerful means for visual art in terms of communication, because the how quickly you can digest number of images at the same time. So we leverage that in this work.
And is there also an explanations element to this work?
Yeah, good question. So we tried a few things in the tools that we broadcast. One of which we do is focus mode, which represent we do very simple things because again we weren't sure if the saliency maps would hold up to this task. So instead we decided to do something very simple. So whenever there's a concept present, we if you click a box, then it will show a box in the whole image to show which part of the image that was most activated by this concept from machine's perspective. So that's the only explanation part of this project.
Okay.
There's also heap map mode, but that's rather stealth mode for now.
That's what?
It's a stealth. It's
A stealth part of the
stealth
project?
part of the project. Not in an exciting way. I should some more work has to be done there.
Got it. Are there other aspects of this studying machines in conjunction with humans that we can talk about?
Let's see. Some of the aspects that I am excited about, and I can tell you a little bit about a few projects that I'm currently working on, and I think that's really exciting next step. So one, we are looking at what sort of behaviors emerge in multi-agent reinforcement learning setting. So if you just let them wild and learn and give them pretty high level rewards, and they are a team trying to work as team, what's the division of labor? How do they learn what to do. So if I build, say, an agent that has 4 legs, intuitively, if we give 2 people a task of let's try to run as fast as we can, and you have this thing, then we would naturally, the first person would grab the first leg, and then the second person will grab the letter two back legs, right? Does that happen in multi-agent RL setting? We don't know. What if we have 10 legs? What if we also have legs and a wheel and a wing? What happens? Those are just really out there curiosity based questions that we're thinking about.
It reminds me a little bit of a conversation I had a couple of years ago with Blaise Aguirre-Yarcas, also at Google, and some of his thoughts on kind of this concept of social intelligence emerging between agents. Is that a collaborator on this project, or is that
Oh,
independent?
Blaise, very busy. I would love to collaborate with you, Blaise, if you were watching
If
this
you're
pod.
listening.
But he's very busy. It is similar, I think, in many years ahead of time. That's completely feasible idea. I wouldn't be surprised that there are some efficient behaviors that are maybe similar, maybe dissimilar with how humans work together. They would emerge in this. Important thing is though that we have to look out for it. We have to
Hmm.
have our right tools to see when that emerges, we notice it, and we confirm or just confirm that it's the desirable thing, that we want them there, and that there's
Hmm.
nothing to be done, or maybe you should do something about it.
Hmm.
Um, I was gonna also tell you about this second project that briefly might be interest to people. There has been a lot of, as everyone knows, that large language model or vision language model has been just impressive.
Hmm.
Frankly, there's been, it might be fair to say, there's some change of paradigm to some extent in the way that we work with these different modalities or one modality in different tasks. So we've been thinking about, in case of say Palm model from Google, and work by Jeff Dean and others. How does it do what it does in that big, giant, yet sparse model? Where does it come from? And if you, for example, fine tune the model to some other tasks, what changes? What really changes? What
Mm,
information resides and what information gets lost?
right.
Uh, that's been something that's been on my mind too.
And do you have early results from that work that you can talk about?
No. The next
Clearly an exciting and important area given the, as you described, the paradigm shift that LLMs are bringing about.
Yeah, and I think Emily, I know you also talked to Emily Bender about whole thing about LLM. I think we need to be careful, and which is why I don't want to make claims about, oh, we have this preliminary results until I really confirm as a scientist. Really confirm, rigorously confirm, and triple confirm to see, okay, this is really it, and then I share it. Otherwise, there's just a lot of information that maybe lack backing, or to only fuel the hype around AI, when sometimes it's fair to have the hype, sometimes isn't fair.
One of the things on that note that LLMs and transformers more broadly are unlocking is this whole opportunity to do multimodal uh, models. What's the state of play around applying some of the work around explainability and understanding to multimodal?
Yeah, it is in its infancy. I think the difficulty, it's difficult to answer that question, because while I see a lot of tools that we developed are on embedding space, for example, this concept activation vector or concept vector, we do everything on embedding space because we know that that's an efficient, tightly learned space that we can do stuff about, intervene, do causal inference. It's a nice space, and that space still exists in this
So it
multimodal
should
models.
extend, right? Is the idea, right?
Ideally it should, but then in a way it kind of shouldn't, because the things
Mm,
what they can do is so different. It must be that some different way of encoding information has happened in this large language model in one way or another. So
hmm.
in a way, I'm optimistic to maybe we can extend these techniques, but on the other hand, we have to be very careful, especially careful because our human biases are amazing. Something that we have and we cannot get over, can escape. And that means because I'm excited about these advances, because I, the developer, are already biased. When we work on these models, we have to be very careful, probably double blind myself when I do research to make sure that I'm not fooling myself. So that introduces additional challenge.
It seems like appropriate caution coming from the author of a paper that said, hey, all these things that we learned about explainability don't explain what we thought they explained.
I learned my lesson the hard way.
You mentioned under the final category that you described, that you were talking through in your talk, around alignment. One of those core elements there is this idea of concept vectors and some of the work there. Can you uh, speak a little bit to that?
Yeah, yeah. It's a line of work that I'm hugely excited about and have been working on for years. So the overarching idea is the following. So prior to concept-based explanation, what we've been looking at are things like saliency map, where I put a number in the pixel, and that's what you're looking at. So if you want an explanation for a picture of a bird, then you look at a picture of a bird and maybe 10,000 other pictures of birds to see, okay, what are the common patterns among the class of birds. What concept-based explanation suggests is that let's not do that, because that's not even how humans communicate to each other. I talk to you in words, that in abstractized words, and you understand.
Yeah.
You're nodding, right? Like I can tell you your glasses, where you sit on a chair. I don't have to explain everything about each pixel in your that I'm looking at you, to communicate what I'm saying. So it's we have a
Mm-hmm.
more efficient, high bandwidth communication. So why don't we build that high band communication with machines and humans? And this concept-based explanation is a first step towards that. So instead of pixels, let's abstractize and use the language that we used with the between humans. So fluffy bird, fluffy dog, or striped, or a circular shaped biopsy, and then cell that looks a little bit oval shaped. That's how doctors can talk to each other. So let's use those abstract, more abstract concepts to have machines communicate to us. And the way we do it is to by building this concept activation vectors. So you say, doctors, give me. I have this medical concept of irregular boundaries in the biopsy samples. I will give you some examples, and we will map those examples in an embedding space, which gives us a vector. There are lots of different ways to do it, but we do it many, many times so that we get some robust measure of this direction and the vector. And once you have this vector, you can do a lot of things. You can ask the model, okay, here's a direction in the embedding space. Do you care about this direction? If I move things a little bit, would your prediction change a lot? Because that means that then the direction influences the model in terms of first order derivative, in terms of sensitivity test. If I remove that direction altogether, what do you do? Do you explode and give up and go home, or you're just fine, like it's as if it didn't have to exist? So by the core concept is simply, the building in this complex concept around medical or human ideas into this one vector, and then so that we can build that this vector can be a bridge between machines and humans communication.
Mm-hmm. In thinking about the concept we discussed earlier around language, that linguistic constructs to enable machines and humans to communicate, and these abstract ideas around concepts, does it support at all the call that some in the industry are making for us to kind of marry symbolic methods for AI and statistical methods for AI?
Yes, absolutely. I know Rao is a proponent of this, and I agree with Rao on this, that uh, in at some level, I think when our principles are just the only way and perhaps safest way to do a task, then I think symbolic based representations would be inevitable, because that's just we decided as a human. We're the human. We're making AI machines. As a human, we decided that that's just how it's going to go. Especially might be important in high stake decisions where we know that this is the way that we've been doing, and we don't yet have better way to do it, we need more empirical evidence until we switch the way that we do things. Then I think that those representations would have to be part of the equation. We can't just do everything in freely distributed representation unless there's some breakthrough that could convince me otherwise.
Mm-hmm. Well, we'll stay tuned for that. Bean, it's been wonderful chatting with you. Thanks so much for joining us and sharing a bit about what you're working on and what you're excited about and what you shared at ICLR.
Thank you, Sam. Thanks for having me.
Thank you.